So let's, so importantly, the point of view we're going to look at is a person outside, and this fairground ride is, I think it's called a rotor or a tornado or something like this. So let's call it outside the tornado to make it more dramatic. So from the point of view of a person outside the tornado, so they see here is basically the top view, the drum, and we've got people standing here against the wall everywhere, and this thing starts spinning faster and faster and faster and faster. Now let's assume this has reached some maximum speed, and this thing is turning at some maximum constant speed. So what is given? We just focus this. Come on. Okay, that seems to be the best we can do. So we are given that those people inside the drum are moving in a circle, right? So we know if we've got circular motion, so we've got circular motion at constant speed, this implies immediately that we must have centripetal acceleration. And we've already got we've got an expression for the centripetal acceleration. We know the centripetal acceleration is equals to the square of the speed divided by the radius. In this case, the radius will just be the radius of this drum. So this is the acceleration from our point of view outside the drum that we know each and every one of these people inside the drum must have, simply because they're moving in a circle, which means their velocity vectors change with time. Change in velocity vector in its direction implies I can get acceleration. Now from Newton's laws, if they've got a non-zero acceleration, there must be a resultant force on them. So the resultant force, let's say this person has got a mass m, the resultant force on that person must be equals to m times a, which is m, and we know what that person's acceleration is, it's just the centripetal acceleration, so m v squared divided by r. So that's what Newton tells us. Yes? Sorry, there? The focus. Font. Oh, must I write it larger? Great, okay. Will do. So we know from Newton's law that's just the resultant force, and that's tied to the acceleration, and we know what the acceleration is. But let's now think about one of these people and think about what type of forces are they experiencing. So if I draw a free body diagram of a person, so let's say here's a person that's stuck against the wall, like so. So there's the wall of the barrel. So we know this person must have a weight downwards. So we must have mg downwards. But these people are not sliding, they're not falling away, even though the floor has been removed. So there must be some opposing force, and what's keeping them up there is actually the force of friction between their clothes and the wall. But that's not the only thing. That gives us the forces in the vertical direction. But we know these people are moving in a circle. So in the direction towards the center of this rotating barrel, there must be a force. because Newton's law tells us we've got centripetal acceleration. These two forces cancel out. So centripetal acceleration means I've got a resultant force in that direction. And all that is, it's the normal force from the wall on the person. And you can now see how this works. The faster this barrel spins, the larger the centripetal acceleration becomes, which means the larger the resultant force is, which means this normal force becomes bigger and bigger and bigger. We know that friction is related to the normal force through that equation. So the normal force becomes bigger the faster this barrel or the tornado spins, which means if this becomes larger, it means the maximum available friction becomes larger. So if this becomes larger, that will become larger. And at some point, this is large enough to counteract the mass or the weight, of this person. So the floor can drop away and that person will stay just right there against the wall, as you saw in the video, stuck, almost as if with super glue. Right, so the trick here is to remember, if you've got circular motion, you must have a resultant acceleration. So that acceleration points to the center of the circular path. And that means you must have a resultant force. So there will be an unbalanced force. In this case, the unbalanced force is the normal force from the wall on the person. Right, and that is now importantly from the point of view of someone that is standing outside this spinning barrel. So the people inside the barrel are accelerating. The person outside is standing still with respect to everything else, so it's not accelerating. And you'll see now we call the frame of reference from which we are viewing this currently an inertial frame, because we are not accelerating ourselves. And you'll see how things change if we view the same problem from the point of view of someone inside the barrel, so someone who is accelerating. And we will call that point of view a non-inertial frame.